Okay, so we have a beam rotating at 4 radians per second with a moment of inertia of 3 meter-newtons. It's going to undergo a collision with a half kilogram mass, a 0.5 kilogram mass, moving at 10 meters per second, perpendicular to the beam. It's going to be an inelastic collision, meaning that the two objects stick together. So the mass adheres to the beam, and you want to find the angular velocity of the system after the collision. Now, in specifying that the collision takes place at a right angle, I haven't specified what path the mass took, okay? The mass could well have taken a path, any path, this path, okay, as long as the direction becomes perpendicular at the instant of, has become perpendicular by the instant of collision. So we could have this representing the beam, this representing the path of the mass. Didn't trace that very well. Okay, now, more specifically, there are two paths that we want to consider. One path could be the one where the mass is in a circular path about the axis of rotation of the beam, in which case we know what its moment of inertia is. In this case, the moment of inertia of the mass has to be mr squared, which is 0.5 kilograms and so forth. And if I did the calculation correctly, it's 1.28 kilogram meter squared. Okay? The other is a straight-on path where the mass moves in a straight line until the instant of collision, and at the instant of collision, the beam has rotated to the point where the mass hits at a right angle. Now, in this case, we know for sure what the moment of inertia of the mass is, so we can figure out the total moment of inertia of the system after collision. We just add the moment of inertia of the beam to the moment of inertia of the mass, and we get this result, 4.28 kilogram meter squared. The moment of inertia has increased by a factor of about 1/3. Now, what happens in the collision? Well, you have equal and opposite forces exerted by Newton's third law between the mass and the beam, and that results in equal and opposite torques because they both act at the same distance from the axis of rotation. So that we get equal and opposite torques, and equal and opposite torques are going to result in unchanged total angular momentum. And maybe I should say total angular momentum, just to be perfectly, well, not perfectly clear, but a little more clear. And when that happens, we can easily analyze the collision now. The moment of inertia before has to equal the moment of inertia after. So we could say that moment of inertia, the angular momentum before equals angular momentum after. Well, before collision, this thing has angular momentum, the mass has angular momentum, and so does the beam. So you can say that moment of inertia of the beam times omega plus the moment of inertia of the mass times its angular velocity equals total moment of inertia times what we'll call the final angular velocity. Now, we do need to figure out the angular velocity of this mass before collision. Well, that's easy. Okay, in this case, we can say that angular velocity of the mass equals 10 meters per second over 1.6 meters. And this is a bit of reasoning. It just goes back to the definition of the radian. A meter of arc, which would be a meter of motion of this thing, on a 1.6 meter circle is 10 over 1.6 radians. Divide the velocity of the speed on the circle by the radius. And that's approximately 6.7 radians per second. Okay, so now we know everything on the left side, and we know the total moment of inertia, so we're going to easily be able to solve for the final angular velocity. Okay, moment of inertia of the beam times omega is 12 kilogram meters per second. There's something wrong with that. Well, in the first place, my units, I'm really bad about writing meter newtons, which is the unit of torque, when I mean kilogram meter squared, because I'm not thinking about my units, and of course I sort of nag people to do this. So without thinking, I wrote down 3 meter newtons and so forth, and it came out wrong, and I didn't discover it until I got down here and my units started not working out. Okay? So this is 12 kilogram meters squared per second. That's moment of inertia of the beam times omega. And the moment of inertia of mass times its omega is what? 6.7 radians per second, 1.28 kilogram meters per second, and now I've got to multiply that. And let's see, that'd be 2/3 of 12 would be 8. And that's like 2/3 of 12. So it's going to be just a little over 8 and 2/3 of 0.08. And it's very close to 8. Kilogram meters squared per second. Because of course, if I've done this right, that's the angular velocity, or the angular momentum that this mass would have in this circular path. Okay, and that's got to equal total moment of inertia, 4.28 kilogram meters squared times omega F. Now it's a trivial matter to solve it. You're going to have 20 kilogram meters squared per second. You're going to divide that by something a little over 4, you're going to get something a little under 5. Okay, this is over 4 by about 1/16, so it's going to be under 5 by about 1/5/16 is 0.3125, I think. So I'm going to say I'd like to say 5.69, 4.69. I'm going to say 4.7, because I think I'm pretty safe with that. Radians per second. Does that make sense? Well, to me, I'm not sure it completely makes sense. Seems like it would go up a little more than that, but that's only half a kilogram. So I'm going to say that, yeah, that's in the ballpark. I would have thought it would have been a little higher, but maybe I'm overly impressed by the effect of this projectile. Okay, well, that's if the thing is moving in a circle. But It could be moving along this path. It could be moving along this path. And you know what? It doesn't make a bit of difference what it was doing before the instant of collision. All that matters is its velocity at the instant of collision. If the velocity at instant collision is perpendicular in direction to the beam, then it's going to be the same as if it was this. Well, in that case, we can say that in either of these cases, assuming the collision being at a right angle at the same point, the moment of inertia of this thing at the instant of collision is whatever this is. In that case, for a perpendicular path, whatever path, as long as it becomes perpendicular here, you have to say that the moment of inertia of the mass is just the mr squared. Now this is subject to the condition that beam mass is perpendicular to the beam. I'm going to put the word if in there, which is the place to put it. Even if it wasn't a beam, if this is some kind of extended object, as long as a vector from the axis to this point is perpendicular to the velocity, you can still say this. You might think through the details of why that is. It wouldn't matter if you had a bunch of other stuff attached to this beam, as long as you take account of that other stuff when you take the moment of inertia. Find the moment of inertia of the beam, okay, or the moment of inertia of the beam plus whatever it's attached to, and we're familiar with that. You're still going to have this. So I say if R mass is perpendicular to B mass, now R mass, okay, R is a vector from the center to the point of rotation, from the axis of rotation to the point of collision. That's our R mass vector. That's our R vector. And R mass here is just the magnitude of the R mass vector. Okay? Your velocity is here. If the velocity and the R mass are perpendicular, we can say this. Now what if they aren't perpendicular? Well, we're going to develop that. It's not hard to develop that, but there are a couple of other things we want to get straight. If they're not perpendicular, the moment of inertia of the mass, and I should have put, I put I mass here. Moment of inertia of the mass equals R cross mv. Now you're supposed to know about the cross product. You're asked to work that out earlier, but you might not at this point, so we're going to develop it in terms of the cross product. And the cross product, if the vectors are perpendicular, is just the product, okay? And the product of R and mv as units of mass times units of mass times units of velocity. Units of distance times units of mass times units of velocity. And that has units of mr squared. Okay. And that's not even right. Okay. So I'm going to erase that. I wrote down the expression for the angular momentum. Just pretend I didn't do that. Okay, so here we have